movement, genius. So there's a gap here which hasn't broken for 150 years or so. In here, if we look at these contours, these are the contours of plate coupling. So where the contours are high, like in the middle here, the two plates are stuck pretty tight together. And where the contours are low, the plates are not well stuck together. And I could ask you again, what's going to happen next? Well, clearly, this is already broken, this is already broken, this hasn't broken for 150 years. We know the rate at which the plate's loading, and we know it's strongly coupled here, and absolutely clearly the earthquake is going to happen here. What we did then was to use these mathematical techniques, the GPS data, the broadband seismometers, and we also used tsunami data to reconstruct what the 2010 earthquake looked like. And of course we expect that this area is going to be the main part that broke. But this is what happened. So the red places are where there was a lot of slip, and the blue and purple places are where there was a lot less slip. Some interesting things. First of all, the earthquake started more or less where we would have expected it. It started in the gap that Darwin observed the last earthquake in. But we have the maximum slip happened exactly where an earthquake happened only a few years ago, and the place where we would have expected the maximum slip didn't slip much at all. So we're getting some things right and other things badly wrong. And the question we asked after this is, how is it that such a simple model where strain is being accumulated in some places, it hasn't broken for a long time, that must be where the energy comes out? Well, we went back to Sumatra to see if we could understand, because what we've done in Sumatra extends farther back in time. Could we explain the fact that that simple model wasn't giving us enough information to forecast what would happen in the Mali earthquake? And this isn't published yet. I think it's really exciting. And again, we're trying to get this into Nature. Here's Thornley's diagram of the 2010 earthquake. Okay? And what I'm going to do is, I'm now going to put the 1797 earthquake on top of it and the 1833 earthquake on top of it. So we have 2010, we have one earthquake in 2007, and then a second earthquake, and there's a gap here. This earthquake released a lot of energy here, then it almost died out, and then bang, it released more energy up here as well. How can we understand that? Well, one way we can do it is put the 1797 earthquake on top of it. Okay? Now, there's a lot of spare information there. I'm only interested really in the red bits because that's where most of the slip happened, so get rid of everything else. And you can see the 1797 earthquake just goes right into the gap between the two parts of an earthquake that happened 200 years later. Then we do the same for the 1833 earthquake. There it is. Again, we're only interested in the stuff that slipped a lot, so get rid of that. And then put all of them together, and what you end up with is that these earthquakes that happened in the last few years appear to be being controlled not only by this simple picture of plates being stuck and releasing energy where they're stuck hard, but they're being controlled by earthquakes that happened hundreds of years ago. So that there's still a footprint of stress on the earthquake fault, which is connected to processes that may stretch back thousands of years. We don't know how far, but certainly the simple picture with the instrumental data that we have at the minute isn't enough to explain all the observations. Okay, now I'm going to rush through the last bit of physics. Some of it gets a wee bit complicated, but what I want to do now is try and see, it's clear that simple models don't fit the data well. How can we take the next step towards taking all the data from all different sources and put it together? Now, I've been asked to formulate the next 20 years. It's an amazing task to do. The next 20 years of earthquake research in the UK. Myself and a guy, former head of department in Oxford, have been asked to do this. And what I think, we don't agree completely on this, so we're still work in progress, as everything is. This, what I'm talking about next, is the general picture of where I think everybody should be going. It's a big scale model in which we have information coming from a whole lot of different directions, and I'm going to describe just the geodetic data, this GPS measurements, and the seismic data, and then there's 20 different data streams that would need to be brought together. So what gives us the current picture of stress? So in a fault, there's stress built up. It's going to break somewhere. It's going to break where the fault is weak and the stress is high. Okay? And if we can understand the distribution of stress, then we may have a good idea of where the next earthquakes are going to be. We still can't predict them, but we know where the energy is stored. The first thing we know is that we don't know enough. So there isn't no matter when you start this work, there's a whole lot of stuff before that we don't understand. The next thing is we know that the plates are being loaded in this heterogeneous way. Some plates are being loaded quickly, some places aren't. There are historical and paleo earthquakes. There are well-recorded recent earthquakes. There's stress interaction between different faults, and there's aseismic processes. How can we put all of this together? I'm going to just wheel you through a few slides now of the main idea. Slip deficit is the amount of stress there is on a spring. If we consider this just to be one part of a fault, we can see that as time goes on, the slip deficit grows until the friction, the force gets too big for the friction, and the block slips, okay? And that repeats. And you can track the accumulation and release of this slip deficit idea over time. You know how that behaves with coupling. Here, where the coupling is strong, the slip deficit grows quickly. Here, where the coupling is weak, the slip deficit slips slowly. Where there's a big amount of slip in an earthquake, the slip deficit drops a lot during the earthquake. And where there's a small amount of slip in the earthquake, the slip deficit only goes down a wee bit. And then you've got this after slip process, which we can add in as well. And then we can do some maths. And basically, this looks really complicated, and the bottom of it actually is really complicated, so we're not going to talk about that. But the initial field is the amount of slip deficit stored at every point, i.e. all over the fault. Okay, if I had more time, I really could get you to understand this. Then you've got the interseismic loading, which is happening because of this. Then you've got the amount of slip that happened in an earthquake is releasing the slip deficit everywhere. And then you've got the post-seismic slip. So if we're going to understand this, we have to solve this equation, not just for one earthquake, but for hundreds of years, including all the earthquakes and all the strain that's been developed over those hundreds of years. If you don't do that, you have no chance of understanding what's going to happen next. The one thing that I wanted to take away from this lecture, if nothing else, is that we're only now getting to a stage, all the work that's been done up to now had absolutely no chance of being able to say what's likely to happen next. And it's only by doing a sophisticated treatment where you include all this information that I think we have any chance of moving to a stage, not of predicting earthquakes, but of saying where the next ones are likely to be. Okay, so I've got some results for you. I don't know if they're right yet. We're still working on them, and particularly we're working on the statistics. But basically, I don't start last week or last year. I start in the first earthquake for which I have reasonably good information. I'm not going to go through all of these, but you can see we've got 31 earthquakes spanning 330 years. Some of the earthquakes we know a lot about, the later ones, you know, the earthquakes that happened in 2008 and 2010. Some we don't know very much about, and I'm using a sort of clever technique where I use a lot of different models of earthquakes we don't know much about, so that the uncertainty in those things are fully developed within the solution to the problem. And where I know a lot about the earthquakes, I only use a few of them. In this case, 1 for the instrumentally recorded earthquakes. And what I do is, I put all the information from all the slip, all the strain accumulation for 330 years, all the earthquakes, and you come up with this picture. Now, this isn't published yet. It's going to be published shortly. We're writing 5 papers at the one time now. It's about 2 years' work, all coming to fruition at the one time. I've presented this at the European Geosciences Union meeting in Vienna 2 weeks ago. It went down really well. I was very pleased. It's really interesting and it's complex. First of all, you can see the island of Siberut is lit up bright red. Here's the slip deficit. It means there's about 11 meters of slip stored there, 11 meters of strain energy. So if that broke, you would expect that the bright red bits would slip about 11 meters. Mathematicians among you will know that you're able to integrate an area like this numerically. And if I integrate this bulge and calculate what the magnitude would be if it all slipped at the one time, it turns out to be about magnitude 8.7 or 8.8. Okay? You'll notice that the colour scale here doesn't just go in one direction like most of the colour scales you work with in school, in geography and stuff, and like most of the colour scales I've showed you up to now. It also has a whiteness to it, and the whiteness measures the standard deviation of the 10,000 models that have gone into calculating this pattern. Where the standard deviation, so I've got 10,000, for each of these dots, I have a value and I have a standard deviation for 10,000 simulations. Where the standard deviation is high, it means that the models aren't giving you the same answer all the time. In other words, we don't know enough to be able to be sure. And where the standard deviation is low, it means we probably have a good handle on the answer. You'll see that the standard deviation, as it gets bigger, you know what standard deviation is, yeah? Variability. Okay. So if you have a low standard deviation, you're pretty sure about the answer. If the standard deviation is wide, big, then you don't know so much about the answer. So under Siberut, you can see the colours are high in slip deficit and low on standard deviation. In other words, we think the strain is big there, and we think we're confident about the strain being big there. Whereas these dots up here actually are big in slip deficit, but they're high in standard deviation. In other words, it looks like there's a lot of strain there, but we're not really too sure about it. And it's this, including the uncertainty within the calculations, that allow us to start dealing with the data in a much more professional way, in which the guys at CERN, for example, are doing all the time. Okay, I just want to, I could talk about this, and I'm aware. Joe, what time is it now?
5:30.
So we've got another five minutes? Okay. I can't stop from just telling you that this woman here is absolutely brilliant. She's the leader of a non-governmental organisation who's devoted her life to try and prepare the people of Padang for the earthquake that scientists like Kerry C and this guy are telling them is likely to happen. Okay? Patra takes all our complicated diagrams and she sort of goes, excuse me, move over. And she, instead of producing diagrams like this and tsunami inundation models with all this massive detail some of the German guys are coming up with, and she just does that instead. This is just the 5-meter contour. This is the map of Padang City. And the 5-meter contour is here. The 10-meter contour is through here. So basically she says, if you're below 5 meters, you're in danger. If you're between 5 and 10 meters, you're still in danger, but not quite as bad. And if you're above 10 meters, you're probably okay. These are not arbitrary chosen contours. They're chosen based on the best science that's been done, but all the faff that we get on with and that we really love, she just goes, I'm not interested in that, because people are not going to be able to include that in the way they plan their lives. There are now evacuation signs up telling people how they should leave the city, and these are neighbourhoods all constructing these things themselves. At the community level, they're really getting people ready so that people are amazingly becoming less afraid of tsunamis because they start to believe that there's things that they can do to protect themselves. So their lives are actually, instead of just living in fear all the time, which they did prior to Patra's work, they're still afraid, of course, but because they're doing stuff that's actually making their lives better. The school work is fantastic. I've been told a lot about this, training kids, and the kids are going home to their parents and telling them what to do, and they're doing evacuation drills within the houses, stuff like that. Okay, government level, non-government level, including journalist networks, so they can get the stories out and use the journalists to do this. Okay, so the Padang story then is a story of complicated mathematical science being used to understand the risk to a real community, and then we're starting this awkward job of trying to help people translate that science into language which is appropriate given the whole cultural setup that I've become really aware that it's not good enough for me to go and give a lecture to people. We need to engage with people and go back to our data and change the way in which we present them so that they become more useful in terms of getting people prepared. And this is stuff we're on the verge, I hope, of getting £3 million from NERC to do this physical science, social science interface work, which is going to be great fun if it comes off in the next month or so, I hope. As a result of thinking this way, I started working with a guy from King's College in London, a guy called Mark Pelling. And Mark is a really interesting social scientist. I thought those two things were mutually exclusive. That shows you the horrible things that training in science does to your head. But I started thinking about what is it that actually kills people in earthquakes. This only took a few minutes, and I think it's really interesting. It's only a week old, 2 weeks old. I've done it with one of our undergrads, a geography student undergrad in the University in Coleraine, a guy called Johnny Kidd, smart guy. Okay, so there are some interesting things. First of all, a big earthquake that shakes the ground really hard doesn't kill anybody if there's nobody there. Now that sounds obvious, but you can't forget that. Another thing is, if you have loads of people and there's no earthquake, nobody gets killed, okay, by an earthquake. The point is you have to include both of those things in your calculations. If you're trying to understand the problem, some people say it's not earthquakes that kill people, it's corruption. That's not true. The ground shakes, that's what kills people. The corruption makes the problem worse. Poverty makes the problem worse. But all of those things you can only understand if you understand, first of all, how people get mixed up and shaken. And if you can get that calculated properly, then you might be able to get some insight into some of the social things which are always going to be more complicated. Okay, so let's see if we can get a measure for an earthquake of how strong the ground shook and how many people felt it. And if we can do some jiggery-pokery with mathematics around that, we might be able to say that was a bad earthquake and this was a good earthquake, including both the people and the shaking. USGS is a great organization. After every earthquake, they produce this. This is a map of the shaking. This is the Tohoku earthquake last year. It's not a very good example, actually, because most of the people got killed in a tsunami, and we're not working with tsunamis in this, but anyway. The seismologists very quickly calculate what the ground shaking would have been like during the earthquake. And then they go for each of the cities, and they use not magnitude, but a scale called the Mercalli intensity scale, which tells you basically how strong the ground shook. And the Mercalli